So Karim got his PhD in 2013 from the Freie Universität Berlin. He's been pretty busy since then. He's proved the Heron-Rotor-Welch conjecture on log concavity of the coefficients of the characteristic polynomial of matroids with Jane Hu and Eric Katz. The Hirsch conjecture on flag triangulations of manifolds, Mullen's G conjecture for for simplicial spheres, and he's been awarded the European Prize in Combinatorics in 2015 and the EMS Prize last year. So I'm very happy to introduce Karim Adiprasito and ask him to give his talk. Karim, over to you.
Thank you. Thank you very much, Peter. It's an honor. I'm a little disappointed that I don't get to go to Durham. I looked at it from the distance or from Google, and it looked quite interesting, but maybe another time. So I decided to set up the talk a little differently. What I will do is, so in my survey paper, I basically gave a new introduction, a new way to enter this this field of combinatorics and commutative algebra and algebraic geometry, and it gives you kind of if you haven't seen this kind of thing before, it gives you a road in. And I thought instead of talking about that in detail, what I will do instead is talk about why, as a combinatorialist, you should be interested. I will talk about applications. Actually, I mean, it always feels a little empty if everyone switches the camera off. So if you don't mind, if you have a camera and don't mind your background, please switch it on it somehow. Thank you. Thanks, Peter. And hi, thank you, Moti, and thanks, Max. All right, so why, as a combinatorialist, will you care about this? Okay, so here's the basic question. Right, so I draw a graph into the plane. Right, so if you're an applied mathematician, you might think of this as locations in the plane, or as a graph theorist, we just think of these as vertices. And then we want to draw as many roads, as many edges between them as possible. Okay, let me try to change the setup a little so that the drawing comes up better. I can add another vertex, and I can add as many of them as it's possible without having them cross. All right, and I'm forbidding something like something an architect, or maybe not an architect. What is it called? Like a city planner would not like, right? Some things like this or this. Or maybe they actually like these type of roads for some different reason, but I'm not going to allow them. So the question is, well, given these many locations, how many roads can I draw? Right? It's a basic, really basic question, and the answer is classical. Right? It goes back to Descartes and Euler. That is that the number of roads between the cities is at most 3 times the number of the vertices. That's it. And the proof is really quite simple. So what you do is you realize that you can always just add edges until every region, even the region at infinity, is a triangle. All right. So now every region is a triangle, including the region at infinity, and then you have the vertices minus edges plus the number of triangles is equal to 2, and you have a simple double counting argument. Right. So 2 times the edges is equal to 3 times the 3 times the triangles, and then you get this inequality. That's it. There's nothing fancy to it. I mean, you have to be a little bit careful with situations where there's just 1 city or 2 cities, but let's ignore that. So that's it. All right. So that's the basic result. Now, first question that you can always ask is, well, how does this work in higher dimensions, right? How does this work in higher dimensions? And I mean, the naive question would be a graph in higher dimensions, but that's trivial. You can always draw any graph in dimension 3, whatever you want. So what do we do instead? Well, we could take a simplicial complex, or some of you will prefer to call this hypergraphs. So I take a hypergraph and I embed it into some higher dimensional Euclidean space. And it turns out that the interesting case, if you think about it geometrically, is really if you embed a simplicial complex of dimension k into Euclidean 2k space. Right, because then the intersection will be transversal. So the intersection, if you kind of imagine them being generic, then the intersection will be points. All right, and this is the most interesting type of intersection. So that's the question. Okay, so how many could you have? And you can again kind of try greedily and just do examples. And the kind of guess that you come up with is that, okay, so for instance, for two-dimensional complexes, the number of triangles should not be more than 4 times the number of edges. But there's a problem of turning that into a proof. And one of the main problems is that now I cannot add triangles monotonically until I reach something that comes from a triangulation of 4-dimensional space. All right, so I can get stuck in various ways, and I will never reach a triangulation just apart from the fact that it will not be a triangulation just because it's a 2-dimensional complex in R4. So it does not really have regions in the complement. So it does not work. So what can we do? Well, it turns out that we can nevertheless prove, under some mild assumptions, that the number of k-dimensional faces is at most k plus 2 times the number of k minus 1-dimensional faces. So we have a k-dimensional complex embedding into R2k in a PL way, okay? Then the number of k-dimensional faces is at most k plus 2. So for instance, if you have a 2-dimensional complex, right, then this means that the number of triangles is at most 4 times the number of edges. And you can give a tighter bound just like you do in the plane, but I mean the tighter bound again, just like in the plane, is just some additive error. So let's ignore that. PL, I mean, okay, what does PL here mean? It's just that you can approximate the map by a piecewise linear map. That's it. Ignore it for now. I will later give a combinatorial definition of that. Okay, so if you're not familiar with PL maps, that's it. That's fine. All right. I should say that that does not solve the problem completely. So for instance, as you see, I give them I impose some restriction on the nature of the map. Right. So that's without that, I don't know. And I also don't know what happens if the complexes are not simplicial. So for instance, you could have a polyhedral 2-dimensional complex built out of hexagons and ask the same question. And you would think that it only gets, that the bound that you have can only get better for you, but it's unclear. The methods don't give it. We don't know. All right, that's it. So this is the type of question that I will address. So basically, I will talk about how this question relates to algebra, how it relates to algebraic techniques. And then my survey paper was essentially intended as an introduction into these algebraic techniques. And so now it's kind of, I will try to write it as a very French introduction. So now you have both. So you have the applications, the motivations that did not quite fit the paper, and the techniques. Okay, good. So if you have any questions at any point in time, just let me know and stop me.
Excuse me, Professor Karim. If we put more restrictions like geometric restriction to embed to be convex, or like this cat 0 or something like that, the problem will be very harder.
If you put more restrictions, then the problem will be easier. I don't know what you want to restrict. Do you want to restrict the complex delta?
Yes.
Or what did you? If you put more restrictions, it will usually be easier. But even for phase-wise linear embedding. So embeddings where you really have a triangle realized as a convex geometric object, all right? So every triangle is linear. Even then, it was not known. So it's not clear. I mean, if it's cat zero, I don't know. I mean, if it has some cat zero structure, maybe you can say something. I mean, if it's cat zero, let me see.
Sorry, I don't want to bother you, sir.
No, it's fine. I mean, the one point is that if it's cat zero, then it will be collapsible, which means that the number of triangles. I mean, cat zero case, you have the stronger inequality, t less or equal to the number of edges, just because it's collapsible. So you have I mean, cat zero is a very strong condition. I mean, it makes a complex contractible. So yeah, so cat zero is just a very, very strong condition.
Thank you.
Yeah. Thanks for the question, Hossein. All
Thanks.
right.
I always follow your papers. I ask it because I know you are working in this cat zero or something.
Yes, but it doesn't. Yeah. Thank you, but it's too strong here. Yeah, thank you. All right. So, what do we have? So associated to every. I want to now go to the algebra. Right. So associated to every simplicial polytope with rational coordinates, there's a rational toric variety. So there's a rationally smooth toric variety. And if you don't remember what that is, it's really not so important. What we want to have is a ring associated to this object. So let's think about the polytope. So for a second, right? So I have my simplicial polytope. So let's say this hexagon. All right. So here's the origin. Then I can draw the fan over that polytope. So basically, I cone over every single one of these faces here. All right. So then I have a fan. And what I'm looking at is the algebra of cone-wise. Okay. So this is a typo. The cone-wise polynomial. So cone-wise polynomial functions on the fan. Okay, so these are continuous functions everywhere, and on each of these cones here, I'm supposed to be a polynomial. Okay, this gives me a nice graded ring. So meaning that graded just means that I have degree 1 functions which are cone-wise linear, so they're linear on every cone, and then their functions are cone-wise quadratic, and so on and so forth. Now, that's an interesting object. Unfortunately, it's much too large for us, and because it's infinite dimensional as a vector space. So what I do is I make it smaller by taking out the boring functions. So the functions that don't have anything to do with the combinatorics of this object, which are exactly those generated by the global linear functions, right? Because I mean, the global linear functions, they don't record anything about the combinatorics. So I take out the idea generated by the global linear functions, and that's it. All right, and this is my object. Another way of thinking about it is I think of this as a simplicial complex. All right, so I think of this my complex my simplicial polytope as a simplicial complex, and then what I do is I take the polynomial ring here where the variables are in correspondence with the vertices. And now what I do is I mod out, basically, first of all, I mod out the combinatorics. So I basically take out the ideal IP, which is generated by those monomials that are not supported. So IP is generated by the monomials that are not supported. Not supported in P. And the ideal theta P is playing the same role as the global linear functions before. So it's basically just the boring functions. So let's ignore it for a moment what the formal definition is, but that's just to make this finite dimensional. It's called the Artinian reduction. Anyway, that's a ring. Okay, so that's the whole mystery object. It's a very beautiful ring. It has very nice properties. I will talk about them a little. And this ring will inform basically much of our combinatorial questions. Every combinatorial questions we want to now address will in some way be addressed, will be in some way encoded in this ring. And I'm sorry that it's my camera is on the same in the same spot as a tablet, so you kind of see my forehead a lot of the time. No. So thanks, Peter, for the question. So this is the ideal generated by the global linear functions. Of course, because it's the ideal, it also includes the global polynomial functions, right? Because every global polynomial is in the ideal of a global linear function. Okay, but also, yeah. Yes, that's right. Okay, Moti, that's correct. That's the Stanley-Wiesner ring. Okay, it's or the face ring of the simplicial complex. That's right. No, we are staying over the reals. Yeah, it doesn't matter which field we are looking at. But I mean, in the end, it really works over any field. So you can do this also in positive characteristic. Let's just come to the convention that we always work over infinite fields. Okay. Infinite fields, this I want just for Noether normalization, but infinite is enough. So if you want, you can also do this over C. For the moment, I want to work over the reals because I want to talk about things like positivity. Okay, so I want to talk about Hodge-Riemann relations in this ring, and the ample comb will have a natural interpretation if I do this over the reals. Okay, so we'll see this. Okay, so that's a ring. Oh, now I have to click this again to go back. Yeah. Okay, so as I already said, it's this ring for a d-dimensional polytope is graded, and the degree d component is just isomorphic to the ground field. So in my case here, it's just the reals. Then in high, okay, so that's the first statement. There's a second important statement that is very nice and very useful for us, and this is that there is a perfect pairing. So if I look at the degree I component and the degree d minus I component, they are isomorphic as vector spaces. And there's more. If I just multiply something in degree I with something in degree d minus I, then this bilinear pairing is perfect. That's it. In particular, this gives you, okay, so this gives you more than just saying that these two spaces are isomorphic as vector spaces. So really, you can think of them, I mean, if you are topologically inclined, then you can think of them as Poincaré as cohomology rings of well, not quite manifolds, but manifold-like objects. So they're rationally, if you think of them from the perspective of rational cohomology, these are manifolds. Okay, all right, and so that's nice. That's a strong property, but the mysterious stronger property, and this is easier to introduce for the moment over the reals. All right, so I have my simplicial polytope P. It lives in the reals. Okay. And now over the reals, I have this fan structure, right? So you remember I have this fan structure. All right, I have a notion of convex cones. And now what I can look at is the cone-wise linear functions that are convex. So I want the function, I mean, okay, so what I can draw is I can just draw the level set as at one. So I draw where the function is one. And then what I want is that the function here draws me a convex polygon. This can be the original polytope, but it can be any other polytope on that fan. The only condition is that it should be, well, somehow, now you have to be a little bit careful. It should be strictly convex with respect to that fan. So clearly it will not be, it's convex linear, so it will not be convex here, strictly convex here. But at every point where the fan breaks, all right, where I'm not inside the cone, I should be strictly convex. All right, and then I have this beautiful isomorphism. All right, so I have an isomorphism between the degree I component of this ring and the degree d minus I component. And now you think, okay, but this I had before, right? I had an isomorphism before. But this is stronger. Okay, so one of the conclusions, one of the kind of combinatorial kind of conclusions that you get from this is that if I write down the Betty vector here, so Betty I for me is just a dimension as a vector space over the reals of the I-graded components. All right. Then what is the conclusion of this theorem? Well, this conclusion will be that the Betty vector is unimodal. It will rise up until some point, until it plateaus, and then it might go down again. That's it. All right. It will not look like a camel. All right. It will look like a dromedar, if you want. I mean, I recently learned that this distinction is not quite correct. But I mean, that's what you should think of. I mean, this distinction is biologically not quite correct. The mathematical statement is what you should think of. All right, so that's already a strong information. All right, so you can think of, I mean, if you think about it like the cohomology ring of a sphere, it's clearly not unimodal. It will not satisfy the Lefschetz property. All right, so this is something that is rather strong. So that's the Hart-Lefschetz theorem. I mean, this will be important for us. And the Hart-Lefschetz theorem, it comes in tandem with another theorem or another property. And this is once I have the Hart-Lefschetz theorem, I can combine it with Poincaré duality, right? To get a pairing not between degree I and degree d minus I, but between degree I and degree I itself. And what I do is I just take A and B and I multiply them, and then I artificially get them to degree D by multiplying with the power of the of this element. And I'm sorry, this should be an L. All right. Okay, this is okay. So then, okay, but then it says something about the signature of this quadratic form. Okay, so you would think, why would you care? We will see later that this, for instance, applied in suitable situations implies that the coefficients of the chromatic polynomial of a graph are log concave. Okay, so this is an important part. So Hart-Lefschetz is not the only thing that gives you combinatorial results. All right. So now the question is, let me ask the question before I motivate the question. And so what you can still do for general spheres, you can still construct this algebra. Okay, so you can still look at the polynomial ring, mod out those monomials that are not contained in the simplicial complex. And if you did this by starting with a homology sphere, so here let's say if I stay over characteristic 0, then it should be a characteristic 0 homology sphere, then I still get a Poincaré duality algebra. So I still have this symmetry. I don't have the unimodality yet because I don't know whether the Hart-Lefschetz theorem holds. So what about the Hart-Lefschetz theorem? And here's an issue. You can show that most spheres will not have this notion of convexity. I mean, that's rather, I mean, this is I mean, if you think about it, so I'm talking here a little bit more generally, but if you think about it, this is just a slightly more general way of saying that most spheres are not boundaries of polytopes, which is really Arlon and Goodman-Pollack, right? So I should actually Pollack. And that's it, right? So that's all there is. So what can we do? Well, I mean, for the moment, I mean, there's no, I mean, unless you have a motivation, there's not much reason to do this as a combinatorialist. But in the end, it turns out that there are several combinatorial motivations. So how do we get there? I mean, first, it's a kind of, it kind of should be, I mean, it's kind of daring to even ask that question. So because, and there's no way that algebraic geometers did not believe that something like this should exist. So I mean, the hard-left-shade theorem is something very deep. It's been around for a very long time, and it's there's basically there's one structure that has been always associated to this, and this is convexity, this ampleness. So it's kind of interesting because now I will show you how actually combinatorialists come to the commit a little vengeance here, because I will show how combinatorial techniques would actually show something more general than what algebraic geometers were able to do. And this is a hard left shades beyond this notion of convexity. By the way, I don't immediately see the chat. It's thank you. Yeah, omega was L. Okay. I don't immediately see the chat, so it's easier if you unmute yourself, or someone if someone unmutes himself once there's a chat, because I don't see it immediately. I try to check it periodically by moving my mouse, but that's it.
I'll try to keep an eye on it, Karim.
Thank you. Yeah, thank you. All right. So, given my talk was coming off, given that I started with the Grünbaum-Kalai-Sakaria conjecture, or the problem, how is this related to the Lefschetz property? So remember we have this. Remember we have the delta simplicial complex that embeds into R2D. And now I'm going to formulate this slightly differently. I'm not going to embed. I will just say, okay, this is a subcomplex of a triangulation sigma of the 2K dimensional sphere. All right. So this is why I actually impose this this PL condition. So if you don't know what PL map is, think of it like this: delta can be realized as a subcomplex of a triangulation of some sphere. All right. So now let's look at A of delta, and specifically first let's look at A of sigma and A of sigma. And we write it twice. So I will look at it in 2 degrees, in degree K and in degree K plus 1. All right, so think of this for a moment. So degree K plus 1, this is generated by the monomials of degree K plus 1, which means that it's related to the number, to the K-dimensional faces, so the K-dimensional simplices, right? The K-dimensional simplex has K plus 1 vertices. Therefore, it's the monomial of it generates exactly the monomials of these K dimensional simplices. They exactly generate the K plus 1 degree component. And then here I have sitting inside this ring as a quotient, I have AK plus AK of delta. All right, AK plus 1 of delta, AK of delta. All right, and there's a nice surjection. All right, so this is a nice quotient. So these are 2 nice quotients. So now what can I say? Well, for instance, I already said that this component here is generated by the K-dimensional faces. So the dimension of this thing here is surely of AK plus 1 delta is surely less than the number of K-dimensional faces of delta. Similarly, AK of delta is less or equal to the K minus 1 dimensional faces of delta. And this is dimension. This is one nice inequality. Okay, so that's one. Okay, so that's, I mean, what I did is, I mean, I basically took a vector space and estimated its dimension by giving you a generating system. The other way around, what I can do is I can estimate the size of a vector space by giving you a generating system and then estimating the number of relations in a rough way. So what I can do is I could look at, for instance, the dimension of AK plus 1 of delta. And then, okay, so what do I have? I have the number of generators. And then, okay, I have to think a little bit about it, but it turns out that the number of relations here is K plus 1 of delta. So it's K, so every K minus 1 dimensional phase gives me K plus 1 relations here. So, I mean, if I combine this here, if I combine these inequalities, then the Grünbaum-Kalai-Zakaria inequality becomes even nicer. Because now, if you think about it, to show the original inequality, which was Fk is less or equal to K plus 2 times Fk minus 1, well, what I have to show now is just a much nicer inequality even, and this is that AK of delta, the dimension of this is larger equal to the dimension of AK plus 1 of delta. And suddenly this is a much more beautiful inequality, right? So there's, I mean, okay, there's not even a factor. I mean, already this inequality is beautiful. Now it's just, I mean, you can't get much better than that. So how would I do this? Well, okay, so here's the thing. The Lefschetz theorem, okay, I know that these here are isomorphic by Poincaré duality, right? Because, right, so this is a 2K sphere, so it corresponds, like ideally it corresponds to 2K plus 1 dimensional polytope. So there's a perfect pairing between degree K and degree K plus 1. So what I want here, right, is the Lefschetz property, which would give me a multiplication, which gives me an isomorphism. But then if I have an isomorphism here, and then I have the surjection in these vertical maps, then in particular, I get that the induced map here is a surjection as well. Okay, right? Just because, okay, so I mean, let's I mean, for combinatorialists, I mean, if you haven't, if you're not used to commutative diagrams, maybe let's take a second, right? So, right, so this diagram is commutative. So if this combination here is surjective, then this combination here must be surjective. All right, in particular, this here is surjective. That's it. All right, so we're good. So surjection would in particular imply this inequality. All right, it would make a surjection makes one vector space larger than the other, and we're done. So far so good. All right, let me now go to how this is proven, and I used half my time, so let me go to matroids for a few minutes and explain that situation of matroids, how this is combinatorially thought about, and then I will go on and explain what is necessary to get to the Grünbaum-Kalai-Zakaria conjecture. What is the difference? Okay, so matroids. I mean, okay, so this is a combinatorial crowd, so I can assume probably that most of you have seen matroids before, right? So the matroids are abstractions of arrangements of vectors, or you can think of arrangements of hyperplanes. You can think of the matroid associated to a graph. You can think of algebraic independence. There are many things that you can think about here. Matroids are kind of ubiquitous. again, if they come from kind of geometry, then immediately that you have this kind of Chow ring associated to it. But you can also, let me go a little faster here, then you can also associate a ring, just like we introduced before, to any kind of matroid. So the trick is to notice that you only have to do it for the largest matroid, and every other matroid is a quotient of that because it's a sub-object of that. And the largest matroid, of course, for a given ground set is the Boolean lattice itself. And what I do is similar to what we did before. So we take a ring that basically encodes all the elements in this lattice of flats. All right, for every element we have one. For every subset of the ground set we have one element. I leave out the entire set and I leave out the empty set. Okay, so I take a proper subsets, non-empty proper subsets. And now what I do is once again I encode the combinatorics. All right. Earlier I took out the things that did not come from monomials in the ring, in the complex. Now what I take out, well, I want to encode the inclusion relation. So what I take out from this, right, is every monomial that does not come from an inclusion relation, right? I will just want the lattice, right? So I take out exactly those monomials here that do not correspond to monomial relations. That's the first thing. And then what I do is, again, I take out these linear relations. Here, think of these linear relations as saying, basically, I don't want to distinguish between any two elements. Every two elements should be the same. All right, so it's kind of a democracy among the elements. They count the same in the ring. Okay. And here's a theorem. All right, so if I have an element L in the interior of the submodular cone on the ground set, all right, so I think of a linear element. I write it in terms of, I write down the coefficients. If these coefficients form a submodular function, then I'm kind of good, but I want to be in the interior of the submodular cone, and then that is good for me. That is convex for me. And then I have, in fact, this notion of hard Lefschetz and the notion of hot Riemann again. All right, that's what I wanted. Hard Lefschetz, hot Riemann. Ignore the more algebraic geometry. If I had more time, I would remark a little bit about why this is somehow very interesting already in algebraic geometry context. But I should notice that here there's still convexity around. Here there's still some notion of convexity. There's positivity around, but there's still the hot Riemann relations. I cannot get around that for the moment. But it's already a start. Here's an application of that, and this is that the coefficients of the chromatic polynomial are log concave, or the characteristic polynomial of a matroid more generally are log concave. And in fact, there are all kinds of log concavity applications. I mean, the trick here is basically use a signature. So basically, it turns out that the hot Riemann relations here, they say that if you look at the degree 1 component, okay, so let's look at the signature of the pairing or in degree 1, right? So on A1 times A1. So what you can think about here, so there's it's negative on this subspace here. So it's negative, the signature is negative on PA1. So that is negative definite, but it doesn't mean that the signature is negative on A1 itself. In fact, there's one positive eigenvalue coming from degree 0. And so it turns out that the matrix is will be the matrix here will not have a definite signature. It will have one positive eigenvalue and all the others negative. And then it turns out that there's a smaller matrix hidden inside this matrix, and this smaller matrix actually encodes precisely if you look at it, the coefficients of the characteristic polynomial, and it will look essentially like this. So actually, this is wrong. So it will look exactly like I minus I plus 1, and then I and ui. And this matrix now will have, well, it will have, we don't know what signature it has, but it will definitely not be definite. It will have a positive, it might have eigenvalue 0, but it will not be will not have all eigenvalues negative or all of them positive, which means that the determinant here will be non-positive, which is exactly the law concavity. That's where it comes from. And that's it. I will not go into the proof very much. Let me just say that, I mean, essentially, we did nothing new here. We discovered that the submodular cone, it gives us a nice notion of convexity. And then we went back to earlier work of McMullen, of Peter McMullen. And essentially what his proof, once we discovered this notion of convexity in this object, goes through. So it's a very nice proof, because what it does is basically he deforms any matroid. So okay, he does not talk about matroids, he talks about polytopes, but what our proof then does is take any matroid, deform it in a nice way to any other matroid, and the hard left shades and Hortima will be preserved. And that's it. It's a deformation argument. And then you only have to show it for special kinds of matroids. But then there is one matroid that you can always check it for by hand. That's the Boolean lattice again. So the Boolean lattice comes in again, and we are saved. All right, so that's all good and nice, but it still uses this notion of convexity. So for the Greenbaum-Kalai-Zakaria conjecture, right? So Milner-Thom and in a most restricted way, Alon and Goodman-Pollack, they tell us that there's no chance we can use this here. There's no submodular cone. There's no analog of a submodular cone. So what do we do? Well, here's the theorem. I will explain this in a second. So I still have the left shades property. So what I take is a simplicial PL homology d-1 sphere, and in fact, the restriction of PL is no longer necessary. I mean, this was already in the original paper, was not necessary, but the proof here actually that I will present restricts to the PL case. But the reason that now, okay, so I might actually not get deep enough into the proof that this matters. So you can actually forget about the PL. Forget about it. I should notice that by now there are 2 more proofs of this that all make kind of use of the same observation, and this is kind of an interesting observation related to the Hall marriage theorem. We will see that. What we will use is kind of an algebraic version of Hall marriage. So I should say that there's a proof by Papadakis and Petrotou in 2020, which works only in characteristic 2. And then we combined forces and gave another proof of the general case in all characteristic. And the interesting thing here is really, you should notice that okay, so the Hall marriage theorem will come in. Hall marriage, and there's another theorem here important importance here. It's called the Laman rigidity theorem. I might I might go into depth of maybe only one of them. All right. Notice also that now instead of convex, right, the keyword convex here is replaced by generic. So generic replaces convex. That's what you should note. So One way of thinking about what we are doing here is instead of giving you a specific isomorphism, a specific marrying between two, all right, a specific stable marriage between two sets, what we will do is basically we will just check the set a little, check the vector space until we are in a generic space. And then once we're in a generic space, we have we have our marriage. That's it. So let me explain a little where this comes from. Oh, okay, yeah, okay. I forgot about the slides with some application. So here's some corollary. So one corollary is that the Grünbaum-Zacharias conjecture holds. That's nice. There is another corollary that is kind of nice, and this is that this is exactly what Peter Cameron mentioned under the atomic models G conjecture. This is that the phase vectors of simplicial homology spheres, they satisfy the same rules as those of polytopes. So what does this mean? Well, so McMullen originally conjectured some rules, some specific rules for the phase numbers of polytopes. So he said only these kind of phase numbers can ever be the phase numbers of polytopes. So you have to look in a certain way. All right. This is somehow he basically gave a description, and he said if and only this description is satisfied, can this be a number of vertices, edges, and so on and so forth of some polytope. Okay. And this conjecture was proven then for polytopes. But then the question was, well, do the same condition hold for simplicial spheres? And this, in fact, one of the corollaries is like that. And then, if you're interested in topology, once again, there are even more applications, right? So what you can look at is you can look at, for instance, restrictions of the number of faces that a triangulation of a certain manifold would have. That is another one. There are several more. There, for instance, they're listed in for instance, a survey paper of mine that I can mention later. Or you can. There's a lecture series that also goes on. So let me go a little faster because there's a business meeting soon. So let me explain how one constructs an isomorphism and why this would be why this is related to the whole marriage there. So here's a lemma, and basically the idea is the following: I want to construct an isomorphism between 2 degrees, right? That's my goal. I have 2 spaces. I want to construct an isomorphism between them. That's the whole that's the Hartlebsch's property. Let's do it on this very abstract level. Right, and so okay, so what do I have? So I have a map that I already have constructed. For some reason I know it. I have constructed it already. So A is my map that I've constructed. And then B is another linear map. Okay, so now what I want to do is I want to take a generic linear combination of them, such that the kernel of this generic linear combination is as small as possible. So the kernel of the combination should be the intersection of the kernels. All right, here there's one very, very simple criterion for this, and this is that the kernel of A mapped under the new map B intersected with the image of A is just 0. All right, so the kernel mapped under the kernel of the old map mapped under the new map intersected with the image of the old map is 0. Then I have this condition, right? And this is okay. So why is this good? Because you should think of this as iteratively marrying off more couples. So if you remember the whole marriage theorem, right? I had 2 sets of boys and girls. Let's be heteronormative for a second here. And they have some acceptable partners, and I want to marry them off in an acceptable way. So I start marrying them off, and then I have a new marriage proposal, and this is my map, right? So I started marrying some of them off. That's my marriage. That's the marriage is A, and then I have some new marriage proposal B. and I want to have a condition here. And this is the linear algebra condition. Now, it turns out that this is exactly the right condition to work in an algebraic setting. Because, why is it the right setting? So we are working in a Poincare duality algebra, in an algebra with a perfect pairing. And in such an algebra, the kernel of the map and the image of the map will be orthogonal complements. So they stand orthogonal on each other. And now what I do, what this says is basically I take the, okay, so now I apply the map B, all right, and this is somehow, this is not really material for me, but now I apply the map B, and then I still will have, if you think about it, an orthogonal complement structure like this. So, but now the question is, right, so when do orthogonal complements intersect? All right, and this is only if the pairing, if your pairing degenerates. All right, if your pairing degenerates in one of these two spaces, then the kernels will intersect. Then these two spaces will intersect. This is an if and only if, right? It's an easy exercise. So let me go back for a second to the Hall-Laman relations. So what were the Hall-Laman relations? So the Hall-Laman relations, they precisely said so there was no longer the condition on the signature. Right? There was no longer plus sign, minus sign. But what it says is that this pairing is non-degenerate when restricted to certain ideals, with restricted to certain subspaces. And that's exactly the right condition. So it turns out that in a linear algebra setting, the right way to formulate the whole marriage theorem is with respect to pairings and non-degeneracy of the pairings at subspaces. And that's exactly what happens here. So this is how you iteratively construct an isomorphism. All right, and that's it. So I mean, okay, so I wanted to give the inspiration for the namesake of Hall in the Hall-Laman relations. I will not explain. So there's another inspiration that somehow kind of in the most basic form explained this kind of explained in a hidden way where this should come from. I mean, this is somehow, it was not somehow, if you look at this or at the original paper or any other paper on this Laman marriage theorem, it's not really aware of this connection to Hall marriage theorem and this Kronecker lemma, but this is exactly what is happening actually. So I mean, if you think about it, that is one way to approach this Laman rigidity theorem. But I mean, let me just say that there is a theorem in rigidity theory, if you know it, and if you want, I can explain it at a later point. You can just hit me up, but so I don't have a lot of time. So this basically says how the Hall-Laman relations give you the hard left sheds in. Actually, there is a jump in dimension. So the Hall-Laman relations in codimension 1. So for d-1 spheres, apply the hard left sheds here for b spheres. And this is why the induction works in the end. I will not go in the other direction. So the other direction now that I wanted to explain is actually where the PL property would come in, but anyway, so because we also said forgot by L, because of time reasons, let me not go over this. It's also a little more topological. Let me just say that if you want to hear more of this, and more details of this, and don't want to read or don't want to immediately start reading the partition complex paper, that survey that I submitted for this lovely conference, then you can look at the YouTube recordings of the Hadamard lectures that happened in April 2021. So it's like 12 hours of lectures, so it's quite a time commitment, but still, that might give you a little more intuition. And let me just close here and open for questions. Thank you.
Thank you very much, Karim. Are there any questions?
I have some questions.
Hussein, please go ahead.
Yes. Thank you, Karim. I have several questions, but I try to just ask few ones. So the first question
you
is,
can also. Yeah.
Thank you. The first question is this Hodge theory stuff that finally one of the results is this Rotas conjecture. The motivation was starting from that conjecture and go to this Hodge theory, or from the original algebraic geometry?
I mean, yeah, the original motivation was to go from the Rota conjecture to the Hodge theory. That's
Okay.
how it
So the
entered for
second,
me, yeah.
the second question is, because I'm not coming from this algebraic geometry and I just started, I'm coming from graph theory. My question is, I have problem with this right artin group. So is it special? Can you put another group? I mean, can you give me, it's a hard question, can you give me a graph theoretical interpretation that why we use this right angle or geometrical interpretation, that why we use this right artin group? Can we use another
I mean,
group?
this is, I mean, the Artin group that didn't actually enter here. So, I mean, this is, I mean, we didn't, I mean, okay, I think you're thinking about something else in terms of graphs, and this is the right angular Artin group associated to a graph. But this is a phase ring associated to the, so what I talked about in the matroid case is a phase ring associated to the lattice of flats. So this is a Stanley Riesner ring associated to the lattice of flats. It doesn't have anything to do with the Artin group.
That's great. And my final question is that you mentioned this Macmillan. Is it Curtis Macmillan?
No, it's Peter. I assume that somehow everyone here is a combinatorialist.
Because
so.
I ask it because I know that Maryam Mirzakhani from Iran was working with Macmillan and he has something about this Kahler manifold. My question was about the rule of this Kahler manifold.
Yeah, but that's not related. So this goes in a different direction. I mean, they are also interested in Taylor manifolds, of course, but they are working in dynamics. So
yes, dynamics.
Yeah. So this is different from the situation here. So I'm sure there's some intersection in topics between their works, but I mean, this is, yeah, this is just the last name, the connection.
So what is the beauty of Kahler manifold in this algebraic geometry?
I mean, Taylor manifolds, I mean, they are very, the beauty of them is just that they satisfy very strong symmetries in their cohomology. The cohomology is very nice, right? So you have something called the Hodge decomposition, and the Lefschetz theorem basically says that this diamond that you draw is symmetric.
I know the decomposition because I also coming from fluid dynamics, so I know it.
Yeah.
Thank you very much. I really enjoyed your talk. That was very great, and I get a lot of ideas. Thank you very much.
Thank you.
So, are there any more questions? I don't see any more. There's nothing more in the chat. So I think we'll call a stop there. So I'd like to thank Karim very much for that presentation. And on behalf of you all, let's thank him. And so the next item is the business meeting in half an hour.